Hey guys, Mr. B here. In this video, we're going to be going over the practice problems for chapter 5.2. All right, so let's get started here with number one. It says, write the electron configuration for each atom. How many unpaired electrons does each atom have? All right, so we're going to need a periodic table to do this. I pulled up this one here, I think it's ptable.com. Just Google periodic table, it's the first one. Otherwise, you certainly can pull up the PDF version that is on Schoology. Either one is fine. So let's insert a text box here so we can get started. So to write this out for boron, we are going to need to find boron on the periodic table. Just go take a look at our periodic table and find boron, which is right here, element number 5. So to write an electron configuration, so this will be for letter A, so boron is going to be equal to, we're always going to start here at hydrogen. Okay, so remember, we're going to start here at hydrogen, which is row 1 in the S block. Okay, first element. So it's going to be 1s1. Then we have helium, which is, again, is right next to hydrogen. I know it's over here on the periodic table, but it is technically part of the S block. So we're going to have 1s1, 1s2, and we're just going to write 1s2 because we're going to shorten it. Then after that, we drop down to the second row. So now we're in the second row. Still, we're in the S blocks. This is 2s1 at lithium and 2s2 at beryllium. So we'll have 2s2. Then we jump across and we get to the P block. And at this point, then we have our boron, which is the first one. So it's going to be 2p1. Okay, and that is our electron configuration. Now, the second part of the question, it says, how many unpaired electrons does each atom have? So for that, we need to probably write out an orbital diagram. So let's go. I'm gonna do underscores. Okay, so underscore. So that's gonna be our 1s. There'll be our 2s, and then we'll go 2p. So let's label these. So this is 1s, 2s, 2p. Okay. So these underscores here are the orbitals, and we're going to draw in electrons as arrows to represent where they are in the orbitals. So let's see if we can do this. Let's do arrow. Should be good. Okay. So let's go. Perfect. Okay. So there's going to be the first one there. And then let's do this again. Arrow. Second one will be here. And we'll lengthen it a little bit. Maybe. Oh, there we go. Okay. So it's just, there we go. It's just a little bit touchy. There we go. Okay. Sorry, I've never used this arrow thing before, so I apologize if it's a little bit weird. Maybe it's better to zoom in. There we go. Okay, so here's 1s1, 1s2. There's the two arrows there for the electrons. Then for 2s2, we have 2 again. So let's go insert again, line arrow. So we'll go up. So there's 1, and then we'll go insert arrow and down. So there is our second one. And then for 2p, we just have 1 electron. So we're just going to have 1 arrow, and that's going to be pointing up or down. It doesn't matter which direction you want to do it, okay? So it's going to look like this. So the question was, how many unpaired electrons does each atom have? So in boron, in this case, we have 1 unpaired electron, okay? These first 2 are paired up, okay? Paired means that there's 2 of them together. In the 2s, those are paired, but here in the 2p orbitals, there's only 1 electron, and that is unpaired. There's no other electron paired with it. So to answer this question, we will say there is 1 unpaired, and we'll just go E minus, okay, which stands shorthand for electron. So, okay, take a look at letter B, which is silicon. So Si. All right, so let's go find silicon on our periodic table. It is right here, element 14. So you'll notice, by the way, that when you write an electron configuration for any element, it's always going to start the same way. So we're going to have 1s2, 2s2, and then we'll have these here, so 2p6. Then we'll down here in 3s, so let's go again. 1s2, so 1s2. Okay, so that's hydrogen, helium, 1s2. Second row, S block, so 2s1, 2s2. Beryllium is 2s2, so 2s2. Then we jump across here to where boron is. So this is now 2p, and this is 6. Okay, so we're in the p block, and it's 1, 2, 3, 4, 5, 6 to get to neon. That's 2p6. Then we go down to the third row, and this is now sodium and magnesium. This is 3s1, 3s2. And then we jump across, and finally we get here back to the p block. We're in 3p. Silicon's the second one in, so it'd be 3p2, okay, as our electron configuration. And then again, to determine unpaired electrons, let's write an orbital diagram. And we'll label them. Okay, so this is 1s, 2s, 2p, 3s, 3p. All right, now a question you might be asking is, how do I know like how many little underscores and stuff to do? That's determined by how many different orbitals there are in that orbital group. So s orbitals, there's only one type of s orbital, right? They're all spheres. So you just have one underscore for that one orbital. For p orbitals, there are 3 p orbitals, whether it's 2p or 3p or 4p. Remember, there's always 3 of them. So that's why we have 3 underscores. And I usually will separate them by a little space to show that they're all in the same orbital group. But we have bigger spaces in between the 2p and 3s to show that they are like separate from each other. Okay, so that's how I know what to put there. If we had to do D, for example, if we had a D, then it would be like 1, 2, 3, 4. Oh, okay, it doesn't work when we run out of space here. Let's do it down below. If I had to do a D, so let's say, for example, we were going to do like, I don't know, 3D or something. We go 1, 2, 3, 4, 5, and I'd label that as 3D, okay, because there's 5 d orbitals. Now, granted, again, we're not doing any d orbitals here, but if we had to, that's what it would look like. So, if you're wondering about that. Anyway, okay, so let's get back to doing our orbital diagram here. So for 1s, we had 2 electrons. So I'll just go up arrow and down arrow. And then for 2s, we had 2 electrons. So again, let's go up arrow and down arrow. I wish I knew the hotkey for arrows so it was faster than clicking, but that's okay. For 2p, we have all 6. So when we do this, it's best to do it this way. Okay, so we're going to go up, up, and up. Then we'll go back and go down, down, down. Okay, because Hund's rule says that you have to put single electrons first in each orbital before you go and pair them up, okay? And then they have to be also spinning the same direction. So that's why we go singles in each one first, and we make sure they're all pointing the same direction. Then we go back and pair them up. Now, granted, even though it's 2p6 and we know they're all filled, it's just a good habit to get into. Otherwise, what's going to happen is, like, for example, we get here to 3p2, and you might want to do this. So you go, oh, 3p2. Okay, so let's go 1 here up, and then let's go 1 here down, right? Let's do it like this. No, that's wrong, okay? You can't pair them up. They have to be separate. So it's good habit to get into to put an arrow in each box first, because when you get to things like this, we know that they have to be separate. Okay, so looking at this, here's our electron configuration. And then as to how many unpaired electrons we have, in this case, we have 2 unpaired electrons. The 2 electrons in the 3p orbitals are both unpaired. So 2 unpaired E minuses. Okay? All right, so that is the first question. And I know that took a little bit there, but hopefully that helped explain a lot of things. So now we'll move probably a little bit faster in our next ones. Number 2, true or false? The orbitals of a principal energy level are always lower in energy than the orbitals in the next higher principal energy level. So this is false, okay? This is basically saying that these energy levels, so like energy level 1, energy level 2, energy level 3, this question here, number 2, is basically saying that the energy level that's above is always going to be higher in energy. And we know that that's not true. Because energy level 3, for example, here we have energy level 4, and then we have energy level 3, and the 4s orbital is lower in energy than the 3d orbital. So this is a prime example here of where even though this is a higher energy level, it is actually lower in energy than the 3d orbital, which is technically the energy level below it. Because remember, energy levels don't actually pertain to amount of energy, they pertain to a radius. So energy level 1 is close to the nucleus, energy level 2 is just a radius that's further away, energy level 3 is further, and then energy level 4, and so on and so on. They don't actually pertain to energy. I know it's confusing. It's just, it is what it is. So, so number 2, this is false. Okay, this is false. Number 3, true or false, as many as 4 electrons can occupy the same orbital. So this also is false because at most, remember, you can only have 2 electrons. That's what the Pauli exclusion principle says. Number 4, true or false, the electron configuration for potassium is 1s1, 2s2, 2p6, 3s2, 3p6, 4s1. Okay, so to do this, we're going to actually check and see where is potassium on the periodic table. We can write it out and then see if this is actually correct or not. So let's go find potassium. And we'll just do this in red down here so we can check it. Okay, so potassium is right here. So it's in the 4th row. All right, so it's going to be 1s2. Okay, so 1s2. Then 2s2. Then we'll have 2p6. Okay, these ones over here. Then we'll have 3s2 with sodium and magnesium. Then we'll have 3p6 all the way to argon. And then lastly, we have 4s1. So it should be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And that is the exact same thing that is in our question. So this is true. All right. Number 5, true or false, the configuration 3d4 4s2 is more stable than the configuration 4d5 4s1. So this one is false. Okay, this is actually false. And as to why is it false, and what is it actually asking? So what is this question asking? All right. So remember we talked about at the very end of this chapter section what makes orbitals stable. Okay, so full orbitals, so fully filled, are the most stable, and half filled are the second most stable. And so when we're talking about fully filled, we mean like s orbitals. Remember that s orbitals can have 2 orbitals at most. Okay, so if it has 2 orbitals as an s, if it has 2 electrons. Most stable. Sorry, I'm 2 electrons. I'm like totally mincing my words here. So s orbitals can have 2 electrons at most. Okay, so that would mean that they are full. P orbitals can have 6 electrons at most to make them full. And so on for the other ones. Let me make this a little bit smaller. Okay. For d orbitals, they can have 10 electrons at most. I can type. Here we go. And for f orbitals, which we haven't really talked about, they can have 14 electrons because there are 7 f orbitals. Each one holds 2. Okay, so 7 times 2 is 14. So 2 electrons is most, is full. 1 electron would be half. For the p orbitals, 3 electrons would be half. For the d orbitals, 5 electrons would be half. And for the f orbitals, 7 electrons would be half. So if we take a look at this one up here, we have 3d4, right? So d4, d, 10 is full and 5 is half. So 4 is nothing special. 4s2, okay, so s2, that's full, so that's good. As for the other one, though, down here, we have 4d5. So d5, that's half. That's good. And we have s1, that's also half. So we have 2 halves. So these are 2 half-filled orbitals versus a full-filled orbital and a partial-filled orbital. And so 2 half-filled orbitals will beat a full-filled and a partial-filled. So this configuration here is less stable than this configuration. This configuration is more stable. All right, number 6, true or false? The electron configuration for copper is this thing here as follows. So let's take a look at copper and see if that is accurate or not. So copper is here. All right, so we're going to write this out together. Again, let's zoom in here just so we can see this better because my font is kind of small. Okay, so copper is here. So we have 1s2, so hydrogen, helium, that's 1s2. Okay, so copper is going to be 1s2. Then we have 2s2, so lithium, beryllium, so 2s2. Then we have 2p6, so we have boron, carbon, all the way to neon. So this is 2p6. Then we're in the third row, so this is 3s block, so 3s2 to magnesium, so 3s2. Then we have aluminum, silicon, phosphorus, argon. This is 3p6, 3p6. Then we have now the fourth row, so 4s2, so 4s2. Then we hit the D block, and remember the D block, even though it's this row 4, the D block is always one number less than the row number. So it's not 4D, it's 3D. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Copper is 9 elements in, so 3D 9, okay? Now this is what we would expect, and that's what is in the problem. It says the electron configuration for copper is this, which is exactly what we just wrote out. However, remember, copper is one of those elements that will move electrons around so that there is a half-filled orbital or a full-filled orbital, and it will be more stable. So even though we would expect this to be the case, this is not actually what copper is. Copper, we're going to copy-paste this. So this is what we would expect. So expected, and this down here will be actual. Okay. Remember that what copper will do is it will take one electron from the s orbital and pull it up into the d orbital so that we have a full-filled orbital here and a half-filled orbital here. That is more stable than this configuration, which has a full-filled orbital and a partial-filled orbital. So even though this is what we expect, that is false. Okay, that is actually not the correct configuration. Correct configuration for copper is this bottom one. So this is false. All right. Write the electron configurations for the following atoms. Okay, so we're just going to write some configurations here. I'm not going to go really slowly through these because this video is going to be too long. So I'm going to go a bit faster now. You have your periodic table on hand, and you can check my work and see if you got the same answers that I did. But for carbon, and I am going to just do this off the top of my head. So again, I apologize if this doesn't make sense to you, but if not, just ask me in class or email me and I can help explain. So it's going to be 1s2, 2s2, 2p2. Okay, and I'm just going to double check that. Yep, 2p2. Okay, this is our configuration for carbon. I'm sorry, for carbon. Letter B for sulfur. Oh, we have two letter B's. All right, well, that's awkward. That's okay. Let's change that to D. For sulfur, so let's find sulfur on the periodic table. Sulfur is here, so it is the fourth one. It's the fourth one in the P block in the third row. So it's going to end in 3p4. Okay, so it's going to end in 3p4, which means it's going to be 1s2, 2s2, 2p6, 3s2, and then 3p4. Okay, that's what it's going to be. And again, I know I'm doing this a lot faster than I was before. So if you have questions or are confused, let me know and I will explain more. But I'm just trying to go quicker so you can see if you got the right answer or not. For potassium, potassium is down here in the fourth row. S block, it ends in 4s1. So for that one, we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And let's, there we go. I was going to say, I try to get this on the same line. All right, and the last one we have is argon. Argon is up here. It ends at 3p6. So actually, here's the cool thing, right? So argon ends at 3p6. So basically all of this stuff right here that we just wrote out for potassium, we can just copy paste this for argon, because that's basically, that's argon. Just remove the 4s1. The 4s1 is potassium here. If you get rid of that one, you have argon, which is, again, why it's kind of neat. So you can just do it right out really quick. So, all right. Lastly, A and B. So identify the elements described below. contains a full third energy level. Okay. Sorry about that. So if it has a full third energy level, what this means is, it means that its 3s orbital is completely filled. So it's going to be 3s2. 3s2. Its 3p orbital is going to be fully filled. So it'll be 3p6. And the 3d orbital will be fully filled too. So it'll be 3d, make sure this is red, 3d10. Okay, so whatever element we're describing here has to have 3s2, 3p6, and 3d10 in its configuration. So all of those have to be filled. Okay, because that's the full third energy level. 3s orbital, 3p orbitals, and the 3d orbitals. So basically, it's not going to be any element that's above row 3. It can't be these ones in the third row in the s block because they don't have any electrons in the p block. So it can't be sodium, magnesium. It can't be these elements in the 3p block because these, argon ends in 3p6. It doesn't have anything in the d block. So pretty much it has to be an element that's down here in the fourth row. And it's going to be an element that is probably, it's probably going to be zinc, because zinc would have 3s orbitals. It would have the 3p orbitals, and it is the last element in the d block, which, remember, this row, even though it is in row 4, is 3d, and it is the 10th one. So this is 3d10. So zinc would be the element that is the first one that has all of its third energy level orbitals fully filled. 3s2, 3p6, and 3d10. So this one is... and basically the answer would just be zinc. I just wrote out the 3s2, 3p stuff just to help clarify the question. But the only answer you would give is zinc. Okay. All right, letter B contains the first p electron. So for this one, it's the first element that basically has the first electron in a p block. And the p block first appears in the second row because there is no 1p. Okay. So it's going to be 2p1. It's going to end in 2p1. So basically it would be boron, because that's the first element that's in the p block in the second row, and it's the first one with an electron there, right? First p electron, so it's going to be boron, so it'll be 1s2, 2s2, and then 2p1, okay? So this is boron. All right. So that is it for this section of notes. Hopefully that makes sense, but if you are confused or need more help, there are videos in Schoology in the helpful videos folder. I would very highly recommend that you watch them. They will help you, I promise. Otherwise, talk to me in class. I can help you, or email me. I can make you a video explaining some stuff too if you really want to. So, all right, guys, that's it for this one. I'm Mr. B. Thanks for watching. See you in the next one. Bye.